So a slightly less familiar question for some, where we've got a rod balanced on two pegs. So let's have a look at this one. So here's the question, and that's the diagram, the 28 degrees to the horizontal, but the rod is being suspended, being supported just by those two pegs. So when we add the forces to the diagram, we have the normal reaction from the top peg, which I'm calling R1, and the normal reaction from the bottom peg, which I'm calling R2. We have the mass of the rod itself. Now, if we start by looking at the maximum value of H, then we've got to imagine that this force is very large, but the rod is still in equilibrium. It's in limiting equilibrium. So we've got friction opposing the motion, or the intended motion. So the friction here will be mu times R1, and the friction here will be mu times R2. We know what the coefficient of friction is, and it's the same for each peg. It's 0.35. So we can add the frictions to the diagram now. 0.35 R1 and 0.35 R2. So these frictions will help us to find the maximum value of H. So I'm going to resolve perpendicular to the rod to start with. And when I do that, R1 plus R2 equals the coefficient of the 2G force perpendicular to the plane, which is 2G cos 28. Not much more I can do with that. I'm just parking that for the time being. Now I resolve parallel to the rod, and I'm calling the maximum value of H, H max. We've got this resistance, friction in the opposite direction, this in the opposite direction, and we've also got the component of the 2G force parallel to the rod, which is 2G sine 28. So when we say H max minus the two frictions and the component of weight parallel to the rod, that will equal mass times acceleration, and it's in limiting equilibrium, so the acceleration is 0. So rearranging that equation, I get an expression for H max, and I've factorized the 0.35 out. So I've got R1 plus R2 here, which is very fortunate because I've got an expression here for R1 plus R2. So from that I can work out that H max is 15.3 newtons. So what about the minimum value of H? Well, for the minimum value, the frictions will now be in the opposite direction. So the frictional forces are now helping H, this force here, which is the minimum value of H, to keep the rod from slipping. So when I resolve perpendicular to the plane, I get exactly the same equation as before. And then resolving parallel to the rod, I get that. So the signs of the two frictional components that we had, which were negative in the previous equation, have now turned to pluses. They're both in the same direction as the minimum value of H now. So rearranging, I get a very similar equation to the previous one, and a much smaller value of force required to maintain that limiting equilibrium. So there we are.